Assalamualaikum. What are we supposed to do today?
Ma'am, we are doing in the secondary effects in BJT.
Sorry?
Secondary effects in BJT.
Secondary effect. Oh yes, yeah, that's right. Where's my book? I brought back my book because yesterday, no, the day before, my book. I hope that's the right book. So okay, let me open. So I need to open. I need to share. Okay. Okay, can you see my screen?
Yes, ma'am.
Better, right?
Yes, yes, ma'am.
Okay, so what we're supposed to do here? Let me see. Okay. I need to look at this. Okay, let's recap a bit. Last class it was only me and Tamana. So my other beloved student weren't there. So maybe my favorite student now is Tamana. No, I'm just kidding. Because she's the only one. So we make a class last time, and we covered this one not before cover. We cover only the important effect in BJT, right?
Yes, ma'am.
So important effects in BJT, sometimes it is called secondary effects in BJT. Okay, it's like normally you don't learn this if it's you just like basic. Now you go to another level, we want to know what are the other secondary effects that affect the BJT. So we have discussed on the early effects. So I think I haven't uploaded the what do you call it, the video. No time to upload. So I hope that hopefully today I can, after this, have a rest a bit. I will try to upload all the videos. It's only the last video I haven't uploaded. Do you know?
Yes.
Yes, right? Okay. So early effect. So I have discussed in the previous class what is early effect and what's the mechanism. The most important is you to be able to explain how early effect happens. And early effect is sorry. Early effects, you need to know the mechanism and how do you get it about early voltage. So in the undergraduate, you learn about early voltage, VA here, right? This equation over here. So in this class, you learn, you understand why you get early voltage. Okay, that's covered in the previous class. Okay, and we discuss only the question is about this, which I haven't discussed, right? Tamana?
Yes, ma'am.
So I'm opening my book. I also forgot. Sometimes things need to refer. In the meantime, Tamana, can you explain the early effect to your friends here?
Okay, ma'am, I can try. We know that the base to collector junction is reverse biased. If we operate the BJT in active mode, we know that it is reverse biased. Do you know that? Alam, Iman?
Yes.
you know that in a BJT, the base to collector junction is reverse biased if we are operating in active mode.
Okay. Yeah.
When
From last week.
yeah, it is reverse biased, the second junction. And we know if we increase the reverse bias, the depletion width will go on increasing at the base to the collector junction. We have a depletion width there, and it will increase. The more we increase the reverse bias, the more will the depletion width increase, isn't it? Like in a diode, what happens when we reverse bias a diode?
The
What
depletion
happens to the
region.
increases, isn't it?
Yes.
So same happens here to this junction, the base to collector junction. When we increase the reverse bias, the depletion width increases, and the depletion width, it goes into the base region more, and it covers more of the base region eventually. You know, the effective base width will decrease. I will send a picture on this WhatsApp, like 1 minute.
It's already in the, I already shown the picture there, Tamana.
Yeah, here.
So you don't have to send the WhatsApp.
Okay, as you can see on the screen, the base to collector junction, if we reverse bias it, the junction width will increase and the junction will penetrate more into the base. Can you see? The junction will occupy more of the base. Depletion region will occupy more of the base, and thus it will reduce the effective base width. Originally, we had a base, ma'am has marked it with pink color, if you can see the base width with pink arrow, original base width. But when we increase the reverse bias, the depletion width will go, it will increase and it will go more and more into the base side, thereby decreasing the effective base width. Do you understand? When the base width is decreased, we don't have much recombinations in the base, and therefore we do not have, therefore we have increase in gain. When we have reduced base width, the recombinations in the base will decrease,
Okay.
and therefore we will have more gain. Because we do not want recombinations in the base. We want the emitter current, the electrons from the emitter to reach the collector. But in the base, some of these electrons got recombined. But now,
Okay.
because of early effect, the base width is decreasing. So therefore, in the base, we will not have many recombinations. Therefore, more electrons can reach into the collector, and we will not have a constant, we will have an increased gain.
Oh, I see.
You
So
understand?
Okay.
I think yes.
I think yes, huh? Okay. So, right, going back to this. Okay, so you think if you do understand, you watch the, what do you call it, the video.
Video lecture.
My brain is working very slow. So
No problem.
we need to, so I will speak slowly. Even my thinking rate also very slow now. Now, okay. So you can watch the video, or if you understand Tamrana's explanation just now, great. Basically, it's just a reduction in the effective base width. Okay, so as the reverse bias increases, therefore you reduce the effective base region. Therefore, when you reduce the effective base region, you reduce the recombination. When you reduce the recombination, what happens is what do you call it? The base current will increase or decrease.
Decrease.
The base current will decrease. So Therefore, so the base current will decrease. Therefore, the base current here normally is straight line, but here there's a slope. Here is a slope because the base current is no longer constant. It's changing with the changes of the depletion region. Number one. That's why the base current, that's why there's a slope there, because the base current is no longer constant. It's changing with the BCE here. Now about the shorter effective base width, therefore higher the NDX. When the effective base over here is smaller, right? So as this depletion region become bigger, so the effective base width becomes smaller. So the blue line over here, right? Therefore, the dN over dx is also higher. Okay. So what kind of current mechanism that's affected by dN over dx? What current mechanism that's affected by dN over dx?
Diffusion.
Yes. So the gradient, the concentration gradient, the current mechanism that affected by the concentration gradient is diffusion current, right? If bigger difference in the gradient or the higher value of the gradient, it means that more diffusion current. So what happens is when the base width here becomes smaller, and the NDX increases, therefore it increases the diffusion current, which is the diffusion current from the emitter to the base, right? So which means that if you look here, the collector current become higher as we increase the VCE. Okay, because you have increased the diffusion current, because the gradient changes now. It's not, the base width is not constant. Okay, so that's the definition. That's the explanation about this here. Any question?
When we increase the BCE.
No. Okay, next. Huh?
Hello, ma'am.
Cannot hear you.
Mana tanya?
Can you hear me, ma'am?
It's like you are shouting behind a mountain.
I don't know what is something is wrong with my computer.
So how? You need to help me. Shout louder.
Ma'am, when we increase VCE, increasing VCE, do we mean that we have to increase the reverse bias for the base collector junction?
Yes, here I explained this yesterday or the day. When BC increase,
Yes,
actually the VBC increase. You need to know. This is from the first year undergraduates. How do you get VCE? VCE is VC minus VE, and you can but you can also relate the VBC in terms of VCE and VEB. So you can play around. So VCE actually is proportional to VBC.
Yes, ma'am.
But reverse bias. Okay.
Yes, ma'am.
Any more question? No?
Not yet.
Not yet? Okay, good. So, breakdown voltage we covered in the last class on the breakdown voltage. BJT also experienced breakdown voltage because it's just a PN junction back to back. It's two PN junction. So if PN junction experience breakdown, so BJT also experience breakdown. So covered in the whole explanation covered in the last class. So this is the breakdown region. When you see the current suddenly increase, that's breakdown. Okay, and this is the normal region. Okay. This one I don't cover, so we cover a bit on this one last class. Now, thermal effects, okay? What is thermal effects? Anybody wants to guess? Guess lah.
Because of the temperature increases and the BJT will get destroyed.
Cannot hear you. I cannot hear you.
I should not answer today. I don't know what is wrong with my computer.
Guess. When you talk, it will reduce me talking. So it will give me some relaxed time if when you talk. If you don't talk, I have to talk. Alam, say something.
Thermal effect, is it the changes of the temperature?
Okay, then continue. Thermal effect is, you know, Alam, you are like one of my friend. She sometimes she just keep quiet, and I say something, and the person just keep quiet. In the end, have to speak. So some people they don't know they goreng they just say something. But you Alam, you just keep quiet. Okay. Right. So or you want to try, Iman?
Ma'am, I
Um,
want to try, but
Let Iman try first.
okay, ma'am.
all this patient. I think it's the effect of temperature towards the efficiency and lifetime of the BGT. Maybe I'm not sure.
Okay. All right. Yes, Tamana.
Ma'am, I think that at the junction first, the power dissipation increases because of the increase in power dissipation. It will get heated up, and because of the heat, IC will increase. The minor will increase more, and because of the increase in IC, power dissipation will increase again. So it will be a process, and until the PGT is destroyed.
Good.
Something like
That's thermal runaway. Okay. So so in thermal effect, it means effect of temperature to BJT. As we know, semiconductor devices are very sensitive to temperature, right? Why?
yes, ma'am.
Because you can have excitation of the free carriers. So when you have excitation of the free carriers, you can have extra current, which you don't want extra current. So thermal effect is the effect of temperature to the, in here we talk about the electrical characteristics. Okay. So the problem is if we, let me draw. Don't know whether the problem or not problem. Yeah, right. So for example, this is our BJT. I have to redraw the forward active mode. So forward. Huh?
We can't see the drawing, madam.
Why you cannot see the drawing? Cannot see
No, ma'am.
Sometimes nowadays I think Zoom is not good. Because it happens also last time, right? Tamana, we had like to
Yes,
go.
ma'am.
I need to stop share and share again.
So Google Meet is okay, but there is no recording option there. Google
Huh?
Meet.
Is it?
There is no recording option for the Google Meet, but
Is it that one? I think.
yeah, there is better one, and there is can have longer conversation, longer
What?
meeting.
Google Meet.
Yes.
Yeah, Google Meet. However, why I don't like Google Meet lah? I don't like the sometimes the quality of the, and it cannot connect directly to my iPad. That's a problem. Because my iPad is like wireless. I'm not connecting it anywhere. So only with Zoom I can connect to my iPad and draw. If Google Meet, I don't know how to do it. There's no way to connect to my iPad for now.
And there is no recording option for Google Meet also.
Is it recording? You
No
can.
recording.
No lah, boleh, can. I know. We can record. I've been recording my Google Meet many times. Normally I do it not for class, for meeting. Alright, so thermal effect. Can you see me drawing now? Yes, you can. So let's draw the forward active. So in the class it'd be great, right? I don't have to draw, you have to draw. Now I have to do all the drawing. So I pity the lecturer. We have to do everything now. Okay, so enough of complaining. Let's do this. So this is the okay NPN NPN. So it be NP forward bias. So forward bias slightly up. Betul kan ni? Yeah, let me. Is that right?
Shouldn't it be different level height?
So normally it should be oh betul lah kan, and so normally it should be there continuous, right? P.
Yes.
So now this N P. So now I want to make it forward bias. So what do? My brain is a bit slow now. So I need to increase it a bit here, right? Or the N is increased.
Ma'am, we have to shift the P downwards. No, up.
Yeah, shift
Yeah,
the P
downwards.
right? So
Downwards.
yeah, because the N should be up, therefore relatively the P is down, right?
Yes, ma'am.
So you're right. Okay, so say here. Should be there. Correct. Then I have the reverse bias over here. I don't have space anymore. So down. So, okay, and PN. Correct? Can you see everything or okay.
Yes, we
Yes,
can.
ma'am.
Okay, so then what do I want to talk about thermal runaway? Okay, so what happens is so what happens is you forward bias disjunction and you reverse bias disjunction. Thermal effect, so you can have thermal effect like normal thermal effect, but it become worse when you want to increase the amplification, right? What's the equation for the gain? Beta equals to
IC by IB. Yeah.
beta equals to IC over IB, right? So if you want the amplifier to increase the gain, you want to make it louder, the speaker or anything, you need to increase IC and you need to decrease IB. So normally you will increase IC, okay? When you increase IC, it means that you increase the forward bias, correct? Right? Because you want to increase IC, you have to increase IE, right? And reduce IB. So what happens when that happens, we need to calculate the power dissipation inside the BJT. Who knows what is the equation for power? Huh?
Current voltage.
Kenapa dia ada banyak kali sama? Huh? Who knows the
Equal IV.
sorry?
E equal IV.
P equals to IV, right? That's right. So in this case, the power dissipation in the BJT will P. Allah, kenapa tak ada dah ni? Habis bateri lah. Ayo, my Apple Pencil suddenly the battery is gone. So P equals to IV, that's a power dissipation. I, that is IC, and V there will be VBC, right? Because the largest voltage that you apply inside the BJT is the reverse bias. Okay, so you will increase, so VBC, the reverse will be high, IC will be high, therefore the power dissipation will be high. So as you increase, you want the gain to be high, you indirectly also increase the power dissipation inside the BJT. When that happens, running out of time. When that happens, as mentioned by Tamana, there's a like they call it positive feedback, right? Loop, whereby then what do you call it? It will increase the current. When you increase the temperature, power dissipation increase the temperature. When you increase the temperature, it increases the excitation of free carriers. Therefore, it increases the current. So then you get extra current IC. IC increase, it will keep on increasing the power dissipation again. So, you don't control the temperature, you will experience thermal runaway. Okay. If you're not careful, you will experience thermal runaway because what do you call it? The thermal runaway is when this positive feedback happens and suddenly you are out of control of the temperature. The current keep on increasing, and in real effect, have you seen anything semiconductor comes out smoke coming out from the IC or any semiconductor device? Have you seen it before?
Yeah, but when it's about to damage or it
Huh?
becomes so much, basically when some smoke comes out, it's about to damage or we
Smoke, right?
already, yeah.
Yeah, I cannot hear you. You're also shouting behind the mountain. So, smoke,
Now,
yes.
if, yeah, when it's smoke, then when some smoke come out from the ICs, so later on we find the IC already damaged or
Yes,
burned.
burn, yes. Normally you will see smoke coming out. It's already burned. And why? Because
Yeah.
it's this effect that happens, thermal runaway. Too much current flowing, and because of and it's a positive feedback. Current increase, power dissipation increase the current again, and in the end you're out of control, then you will burn the device. Okay, so that is thermal runaway. Another thermal effect that we should consider is, so this is number one in the slide. So I will add some another thing which is not in the slide. Another thermal effect that you need to consider is that number one is thermal runaway. Number two, remember when we learned before in the semiconductor device early chapters, right? What happens if you increase the temperature inside a semiconductor material?
Conductivity increases.
Minority carriers.
Increase or decrease?
In free carrier, there are more free carriers, so should increase the conductivity.
Yes, but there's another effect. That one done. We already talked about the free carriers. Another thing that we haven't talked, the effect of temperature to the free carrier. We discussed this before, I think.
If the semiconductor is highly doped, then it will increase in temperature will result in reduction of the conduction.
So we're talking about temperature, right? So
Yeah, like in metals, because highly doped semiconductors behave like metals, so they also have a negative temperature coefficient.
no, I'm not talking about that. We didn't discuss that, I think, in the class.
Then
We talk about scattering, right?
scattering. Yes, ma'am.
Yes.
So can you explain that?
Yes, that's scattering. The resistivity increases because the collision.
Yes. So that's an effect. That's why I said whatever we learned before, you cannot erase the memory because we keep on using it again and again. That's the basic. When we started, that's the basic of the physics. Now in the device, the same thing will happen. If you increase the temperature, you number one, what mentioned by Iman just now, you can have extra excitation or generation of free carriers. And number two is in the same time, on top of that, you also have lattice scattering. And this lattice scattering will become worse due to high kinetic energy because when you increase the temperature, the lattice will vibrate more, right? Therefore, so lattice scattering collision become more, will increase. Okay, so therefore it reduces the conductivity and hence it's supposed to reduce the current. So in the same time, in what do you call it? In the same in the same situation, there are a few mechanisms that's happening. Number one is scattering, and number two is this increase in the free carriers. So both will compete. Okay, this both mechanism will compete, but in the end, if the excitation more than the collision, what happens is it will increase the current. How about lifetime? Okay, let's talk about lifetime. Okay, the way we discuss, the lifetime is what is lifetime? Anybody know what is carrier lifetime? Have we discussed this before? Yes, right.
No, ma'am, we didn't discuss.
No, previously, like starting of the course, no? Carrier lifetime when we talk about defect, no?
Maybe, I don't remember.
Okay, carrier lifetime is what do you call it? Okay, this is very interesting. Carrier. What is carrier? What is the carrier?
The electrons at holes.
Yes, correct. So the electron holes have lifetime. Lifetime means lifespan. So you, me, Tamana, Alam, and Iman, and me, we have lifetime. So when we die, we finish our lifetime, right? And the lifetime is being determined by God, by Allah. So electron and hole also have lifetime. So that's why Allah said, nothing in this world will be there forever. Only Allah will be there forever. So how does electron hole, we call it die or disappear? It's when so lifetime is considered when starting the carrier becomes free. So remember when the carrier is in for example electron, if it's in the valence band, it cannot move. So we don't consider the life is living, it's not free. When it becomes in the conduction band, so the lifetime starts. So it can move in the conduction band. How long it moves in the conduction band is the lifetime. Whenever the carrier recombine, then that's the end of the lifetime. Okay, whether it recombine from band to band or recombine from band to the defects. Okay, that's lifetime. So is the basically is the how long a free carrier stays free. Okay, so before is recombined. So what happens is the lifetime of free carrier normally will increase due to re-excitation from recombination centers. Okay, now we're talking about BJT with defect. So we have BJT over here. Maybe we have the trap center over here. So with temperature, with defects over there, it will further further ease the generation of free carriers, right? So if there's no defect, it's more difficult to excite. But if there's defect, then it become easier. Plus, so if this is the trap level, defect, some defect are empty. Defect is like a trap. In the trap, like a hole. Hole you confuse with electron hole. It's like if it's a well, sometimes the well is empty, sometimes it's filled, right? So the trap is also like that. Sometimes the trap is empty like this, but sometimes the trap is already full. It's already trapping something and it's stuck there. Sometimes it's stuck, okay? It doesn't go anywhere. But with temperature, with thermal effect, this stuck electron can be what do you call it? Re-excite. Okay. Sometimes there are too many. There are many defects, and many carriers are stuck inside this trap. So when we increase the temperature, okay. Let's continue. Where did we stop? Or where did the Zoom stop me? Hmm? Are you with me?
Yes, madam.
Apa gelap ni? Limaza. Kenapa dia gelap ni? Awak nampak gelap ke?
Gelap. All black.
Something wrong. Oh ni, nampak dah. Kan? Nampak dah?
Dah. It's fine now. It's okay. Now
Alright.
it's okay.
Kat mana kita tadi ya?
Traps in BGT.
So, okay, maybe like that. Okay. So, I was talking about defects in BJT. So, you can have re-excitation. The word is re-excitation. Re-excitation of free carriers from the defect. So, therefore, what happens is okay, so beta equals to IC, okay, sorry, that's on the top. So beta equals to IC over IB. When you have re-excitation of free carriers here, you will increase IC. Okay, so IC here will increase, therefore beta will increase, right? So if the beta increase, therefore you increase, because now we want to talk in terms of beta of the gain. So that's on the lifetime. So there are, as I'm talking about, there are few mechanisms that are happening. Number one is lifetime of the free carrier. So when this happens, right? When this happens, re-excitation happens, it increases the lifetime. Why? Because then suddenly the electron are alive again. Okay, you only lose, the carrier only dies when you go when it goes to the valence band here. So you increase the lifetime, therefore beta increases. Number two mechanism is the mobility will decrease because of the scattering. So when you have scattering increase, mobility decrease, right? So when mobility decrease, the current will decrease, therefore beta decrease, right? So there are two mechanisms over here. Number one is due to re-excitation, and therefore we talk about lifetime of the carrier, and the other two is on the scattering and mobility. There are two competing mechanisms. But generally, if this lifetime dominates, this mechanism dominates, you have more free carriers due to the defect and also excitation of the free carriers from the band to band, you will get thermal runaway, and it's a destructive to the device.
Madam,
Yeah.
Alam asks to let him join.
Okay. Saya dah record ke belum?
It's recording now.
Okay, thank you. Alright, any question? That's on thermal runaway and thermal effect. Ada soalan? Any question?
Ma'am, I think will the lifetime of electron will be equal to the lifetime of hole because they will be created simultaneously.
Okay, good question. If it's band to band, like let me draw. If it's band to band like this, electron goes here. You have electron hole pair. So if let me draw it better. So if it's band to band, you have excitation of electron over there, and you have hole being excited to the here, right? So if band to band, you get electron hole pair. Yes. However, if it's re-excitation from defects, okay, if the defects, there's defect ni, I don't have anywhere to draw. I will draw it here. This defect, there are different types of defect. So as I mentioned, when you have the the trap level, you sometimes it's empty, sometimes it's filled. When it's filled, it can be filled with electron or hole, right? It depends on type of trap. So depending on the type of traps, sometimes you have extra more electron and sometimes you extra more hole. So how do we know the trap is like trapping electron or hole? We need to do experiments. Then from the experiment, we know the defects that in our material is a defect that trap hole, and sometimes defect that traps electron, or sometimes both. Okay. Have I answered your question, Tamana?
Yes, ma'am. And one more thing I want to know, when electron hole pair is generated, when they are generated, and
Iman
electron and
cannot hear you. I cannot hear you. Maybe Alam can hear you because he looks happy.
No problem. Same. I also sometimes cannot hear.
Okay. Alright, Tamana, you need to speak louder.
Okay, ma'am. Ma'am, when electron hole pair is generated, and after this their lifetime is over, then will the electron recombine with the same hole from which it was generated earlier, or they can combine with any hole?
Good question. So like human being, you want to remarry, you don't have to marry the same person. You can marry other people. No, you know what my supervisor explained about electron hole. But he's a non-Muslim. The way he said, that's why he said free carriers cannot be put close together because they marry, right? So they say so it's like pair because electron and hole are pairs. Okay, I need to charge my. So electron holes are pair. So when you want to recombine, it can recombine with any what do you call it, any free carrier, any hole. It's okay. Okay, any more questions?
Yes, ma'am. No.
What he was stating something like that. I think very interesting. Electron hole as if they have their own life and they are living, actually living things, you know. It's a creation of Allah, this electron hole thing, and they are happily, and they can also marry. They also can
Yeah,
die.
Allah subhanahu wa ta'ala has created everything in pair.
Yes. So electron also want to fight, and the pair, and they are, and the interesting about, they want to recombine, and they always want to recombine, right? If there's a chance of recombination, they will recombine. That's why if you so the same as human being, we like to recombine. That's why Islam put rules so that you recombine only at the right what do you call it, situation. You can only recombine when you get married. If you are not married, you cannot recombine. But electron hole, they recombine wherever they like, like the animals. Huh? Okay. Any more question?
No, ma'am.
Okay, let's go to the next one. What's the time now? 3:11. Base resistance. So what we have the effect. Let me go through what other things that we need to cover. How many classes we have left? This is week 11, right?
Yes.
11, 12, 13, 14.
6 classes.
Eh?
6 classes also.
Tak dengar.
6 classes.
6 classes. Including this one?
Not including this one.
Oh, we have 6 classes. Let's minus the last week. No, so we have 4 classes. So let's see, 4 classes. 1, 3, I will not cover this band gap narrowing. Maybe I should. I don't know. I never covered this. Webster effect. I normally I skip the Webster effect. And then after that, next slide is only MOSFET. MOSFET normally I can cover in one class or one or two. So we have two more classes on BJT. If we have two more classes on BJT, so 3, and then two more classes BJT. We have a lot of time. Maybe we should end our class early today. So because not much to cover. We only have this a few more. Base resistance for and then we have base resistance emitter crowding. This is not much. Little than current gain is this will is together with the Kerr effect. Only the Kerr effect maybe takes sometimes a bit difficult to understand the what do you call it, the physics. Then depends on whether I'm energetic or no. If not, we skip the band gap narrowing and Webster effect. Then we have only the MOSFET after that. Do you want to cover? Huh?
Can you please upload the videos on YouTube? I mean, the classes on BJT.
The classes on BJT?
Yeah, can you please upload the videos on YouTube?
The last one?
Yeah, last two classes.
Oh, I haven't uploaded the last two classes?
I have checked, yes, bro.
Oh, okay. Inshallah, I will do that. I'll upload the classes. I think we should end here, and then next Monday will be another quiz, right?
For photoelectric devices.
On optoelectronics.
Yes.
Next Monday on optoelectronics, it'll be another 30 minutes. You need to take your own time somewhere, somehow. By the way, I have a bad news. Bad news. I couldn't find your quiz one. So I mean, because of this PKP thing, I tried to, maybe because I carry everything to the house. I tried to I thought it's in the office, but it's not in the office. I'll be looking at it. So can we decide that let me stop sharing here. Can we decide